sphere map. In the previous video we learned about the cube map, and now in this video we will learn about the sphere map. When the cube map stores the surrounding environment on the faces of a cube, the sphere map stores this entire environment on a disk. Let's first see how that image of a disk is created. So we create it by capturing the reflections of a sphere. So we have a reflective sphere, and you can see that these reflection vectors actually point to all different directions in the environment. So when we take a picture with an orthographic camera of one side of the reflective sphere, then theoretically we have the values for all the different reflection directions. One cool real-world way to actually capture a sphere map is to take a photograph of a reflective sphere. So here I have this Christmas ornament, and I just took a photo of it with my phone. Now my phone, of course, is not an orthographic camera, so there is going to be some distortion in it, but in principle this is basically your do-it-yourself sphere map. Historically, this was also one of the first cases that people created a sphere map. They used a Christmas ornament exactly like that. They took a photo of it with a film camera, and then they imported it into a computer and used it to sample the reflections for their 3D model. So the sphere map itself is just this disc-shaped cutout of the Christmas ornament, and we can put it on a 3D model to sample the reflections from. So this is the Utah teapot by Kenzie Lamar. Well, the Utah teapot is actually a very historical 3D model, but Kenzie has made it available through Sketchfab, and I just sampled the reflections for this teapot from the sphere map I captured with my phone of a Christmas ornament. So this is what it looks like. So how are the values actually stored in this sphere map? We can think of it as a space from -1 and -1 to 1, 1, where each of the coordinates specify the x and y coordinates of the normal vector of that sphere. So imagine a coordinate up here. So this is going to have the coordinates 0 and 1. So this is going to be a normal vector pointing up. Or the coordinate on the right here is going to have the values 1, 0 pointing to the right. So how do we sample this? Well, first we want to find the reflection vector r in camera space. We have the camera over here. We have the incident vector, the normal vector, and the reflection vector r. So this is exactly the same that we did with the cube map. We reflect the incident vector over the normal vector, and we get the reflection vector. Next we want to move the vector r into world space, otherwise we will have the same issue that we had with the cube map before, that the reflections are always in relation to the camera. Instead we want them to be in relation to the world, so we take the camera's model matrix, we multiply a reflection vector with it, and we get the reflection vector now in world space. Now we think of this vector r in the sphere maps space. So this vector r, this is our reflection vector in world. We want to sample our sphere from the coordinate where this reflection vector r is the same that we have in our 3D world. So in our minds we kind of move that reflection vector r from the world to this sphere map space now. But in the sphere map space the coordinates are indexed by the surface normal. So we want to know what is the surface normal on that reflective sphere that corresponds with our reflection vector. And in the sphere map space, because we saved the values with this orthographic camera, then our view vector in the sphere map space is just 0, 0, 1. So we have this right-handed coordinate system, x is to the right, y is up, and z is well towards the camera. So to find this normal vector, we just add our reflection vector and the view vector together, making these two sides of this rhomboid, and if we normalize the result, then we get the normal vector that lies on the diagonal of this rhomboid. So that is the normal vector that corresponds to our reflection vector in the sphere maps space. Now of course our sphere map is actually in UV space, so the coordinates are not from -1 and -1 to 1, 1, but from 0, 0 to 1, 1. So we remap that normal vector's x and y coordinates from -1 to 1 range into the 0 to 1 range by just multiplying it by 0.5 and adding 0.5. And that is going to be our sample coordinate for the sphere map. Now there is a big limitation with the sphere map, and that is that we have the high quality data only on the side or the angles facing the camera. You can see here that this teapot and this sphere are rotating, and when we have the reflection angles as these grazing angles or even the point exactly behind the camera, then we are losing the detail on the sphere map, the granularity is getting less and less, and then we have this aliasing and this kind of a blind spot exactly behind it. And these are the values that are kind of represented on the edge of the disk. So there is very little data, very little resolution to save that data onto the edge of the disk. So this is where the sphere map kind of breaks down. So from this video, you should understand the sphere map, its storage of the environment's illumination, ways to create one, ways you can create one yourself by taking a Christmas ornament and just taking a photograph of it. Then we saw how to sample the sphere map, what is the math behind actually sampling the correct coordinate from the sphere map, and we saw its limitations. Namely, that when we are rotating the camera and we want to sample the reflections from larger reflection angles, then, theoretically the data should be there, but because of the low resolution around the sphere map's disk, there is aliasing and the sphere map breaks down there.